we're going to be talking about the difference between flow rate and speed. So for an analogy on this, we're going to use a river. Let's say that we have a river. It's a constant depth everywhere. It starts off here at position 1 where it's nice and wide, and then it starts to get narrower here at position 2, and then it gets super narrow there at position 3. So I want you to think about two things. I want you to think about how the flow rate, which is the amount of water passing one point every second, compares at position 1, 2, and 3. I want you to make that prediction. Pause the video if you need to. And then I want you to think about the speed of the particles, which is the rate at which the particles are traveling at position 1, 2, and 3, how those compare. And make that prediction before we continue. Hopefully you've made your predictions now. And let's think first about flow rate. So flow rate is the amount of water passing one point every second. And we know that this river has a constant depth. And we know the water is not spilling out over the banks, and so it has to stay in this channel. You'll see that positions 1, 2, and 3 have different widths, but in order for, let's say maybe, I don't know, 10,000 gallons of water passes position 1 in 1 second. That 10,000 gallons has to also pass position 2 in 1 second. And that same amount of water has to pass position 3 in 1 second. Because if it didn't, it would overflow the banks. Or there'd be, like if it went slower here, or if it had a lower flow rate, it would, there would be like a gaping hole if there was a lower flow rate in the back than in the front, which isn't going to happen in a river. So everywhere along this river, there has to be the same flow rate. The same amount of water goes in as comes out because it's not overflowing and there's no like gaping hole in it. So flow rate should be the same everywhere. But when we think about speed, it changes a little bit. So let's think about 8 water particles. 1, 2, 3, 4, 5, 6, 7, 8. So I have my 8 water particles at position 1. They all have to get past position 1 in, let's say, 1 second. They don't have to move very fast because they can all be next to each other. But then at position 2, it's not as wide. So now we have to have the particles like this, behind each other. So now to get past position 2, they all have to get past position 2 in the 1 second, but they have basically 2 rows of them that have to get past that point in 1 second, so they have to move faster to get through there. At position 3, it's even narrower, so maybe there's only 2 particles that can fit next to each other. So now to get past position 3 in 1 second, all 4 of these columns of particles have to get past position 3 in that 1 second, so they've got to move even faster. So the particles at position 3 have to move the fastest. The particles at position 2 are the medium, and the particles at position 1 can move the slowest. So when we think about when you're checking your predictions, our flow rate should be all the same. And then our speed, 3 is bigger than 2, which is bigger than 1. When we apply this to our electricity, we are going to think about the flow rate of charges. And we focus a little bit more on the flow rate than the actual speed of the charges. Flow rate is what we care about. And within a circuit, we have the same idea where the charges can't bunch up on each other and they can't spread way out. So they're just all pushing each other along. And the flow rate should be the same throughout the whole circuit, which is what you found when you've been doing your experiments with your little compass. You're looking at the deflection at different parts in the circuit, and you should see the deflection is the same in one single continuous loop. Yeah, that's it. Good job.